Okay, so I'm going to take the data for the balloon lab. The balloon lab is basically using the ideal gas law to calculate the pressure and the number of moles in an inflated balloon. It seems like a very, very simple idea. The only problem is you're being asked for two variables. You're being asked for pressure and moles, that's two variables, and you can't really solve for two. So I'm going to lead you through this. I've got this mock-up oversized version. I'm going to lead you through the numbers. You're going to have to write them in yourself on your own paper. And it's kind of cookie cutter. You just follow the directions. I'm not going to give you everything. And you're going to have enough to be able to calculate the moles and pressure. But it's still not going to be easy. And you notice that the very first thing it tells you is to measure the mass of the uninflated balloon. So let's turn our balance on to get a mass, and we want to make sure not to forget to do that. Here's an uninflated twisty balloon, the kind you make like twisty animals out of. Okay. Oh, it's not the spherical balloon, it's the twisty balloon. It's the twisty balloon from this can. Okay, so let's see what the mass is. You got to make sure it's all resting on top of that balance pad. 1.18, and the unit is grams, of course. The units are sometimes on here, but don't forget what your unit is. Okay, also don't forget to write your name on it. And that's the mass we're starting with. So this is the uninflated balloon. Okay. Now, the next thing I'm going to do is inflate it. Inflate the balloon. Okay, so now we are here. Inflate the balloon. Blow it up with the pump. Now the reason we're using a pump is because a pump will actually insert the air from outside. The air that's in the room gets pushed in through the pump. And so, oh yeah, one thing, if you do this experiment yourself, one thing I highly recommend is stretching out this last 2.54 centimeters. Okay, this last little section here, just the part you're going to tie. Of course, I'm trying to stay metric. You can probably imagine what that is equivalent to in the crappy standard system that we use in the US. And then I'm going to inflate this balloon. Now, normally I would inflate it out away from everything, but I want you to be able to see it inflating. Notice as I inflate it, it's kind of like a long cylinder, isn't it? It's kind of like one of those shapes. And I don't want to inflate it to the very bitter end, because if I inflate that last little bit, it'll be too hard to tie it. I want to leave just a little bit there, just a tiny little bit at the end, see that? And that's just so that I can have enough leeway to tie the balloon. If I didn't leave that on the end, then it would definitely pop. I hope it doesn't pop. And I've just got to feed this through here to make sure it doesn't deflate. Okay, now the problem with these balloons is a few problems. One of them is that they can easily pop, so I want to get my measurements before it does pop. Another problem is it's not consistent along the length of it. So what I want to make sure to measure is about where it's average. We're assuming that the whole balloon is basically a cylinder, and if we know it's a cylinder, well then we can find the volume of the cylinder using this equation, the volume of a cylinder. There's a little bit of an issue on the ends. Okay, that's not really a cylinder on the end. Cylinders don't have those on either end. And there's that, well that doesn't add up to much. Inside the plastic there, probably, definitely less than 1 milliliter inside there. So that's not, we're just not going to worry about that part. But we will concern ourselves with these in a moment. In order to get the volume of this balloon now, what I'm going to do is I'm going to measure for a cylinder what I need. It's pi r squared times h. So I need my r and I need my h. Okay, h is pretty obvious. H is the length. It looks like this one is longer than a meter. So that's why I have this little tape here. Notice how I'm going to measure from just where the curvature stops there. I'm going to straighten out the balloon. Sorry about the noise. And I'm going to get the number of centimeters to about where the curvature stops on the other end. What would you say that is? Right about there. I would say about 108 centimeters. 108 centimeters is my H. Okay, that's my H. Now what about my R? Okay, well, it's kind of hard to get in there. It's kind of hard to get in there and measure R because it's inside the balloon. Okay, notice that there's no easy way to get in there. You can sometimes try to eyeball R and say, well, it's It's a little bit less than what it looks like there. It's a little bit more than what it looks like there. You could try it that way, but that's not a very accurate way to measure radius. But we have a neat little mathematical trick that we like to use for finding radius, and it's a good way to get a very accurate radius, and we're going to use the circumference. Now the circumference of a circle is all the way around a circle, and the definition of pi is actually the ratio between the diameter and the circumference. So if we can measure the circumference, we can easily find the diameter by divide both sides by pi. And we can even go down to the radius, because of course radius and diameter are very closely related. Radius is just halfway across the circle, diameter is all the way across the circle. So how am I going to get the circumference? Well, I'm going to use a piece of string. I could also use that tape measure, but for a smaller circumference, I find that the string works easier. I'm going to pick about, well, it's a little thinner over there, it's a little thicker over there. It looks to me like this is about average. So this is going to be the approximate circumference. Now notice, right where I meet the edge of the string, I'm going to pinch it with my finger. I'm not going to let go. I got to set my balloon down carefully so that I don't pop it accidentally before I get all my measurements. And we've got, just under, no, it's right on the 12 centimeters, boom. It could have been 11.9, 11.8, but honestly, it looks like it's right on the 12. It just happens to be. Okay, so that is my circumference. That is not my radius. That is not my diameter. So now remember, you've got that for circumference. Where does that go? That goes right here over here. That's your circumference. So now you have to use the circumference to get your diameter, and then you have to use your diameter to get your radius. Okay, and then we also just measured the height. That was the first number we measured. So we just measured these two. You have to calculate those two. Well, using those, you can plug them in to get the volume of your balloon. You can plug those in to get the volume of your balloon. Before we talk about that, I want to get my other measurements before the balloon pops, because we want to get everything we can, every piece of data we can to help ourselves with this equation. Now, temperature. Well, again, I can't get the thermometer inside the balloon, but if I put it against the balloon, as long as it's been inflated for a minute or two, I will at least get the temperature of the material the balloon is made of. And then, of course, if I get the material the balloon is made of, it's probably the same temperature as what's inside. And honestly, it's probably the same temperature as what's inside the room. And it looks like it is 22.5 Celsius. I don't know if you can see that. 22.5 Celsius. But of course, Celsius is no good in these kinds of calculations. What do we have to do with the temperature? We have to turn it into Kelvin, of course. So don't forget, you got to turn that into Kelvin. Let me put the balloon down again for a moment. I'm taking a bunch of risks here with this balloon. Okay, so what I just recorded there, I jumped ahead slightly. I'm actually right here, the temperature in degrees Celsius. And then you're going to have to convert that into Kelvin, of course. That's something you're going to do. Okay. Oops, before I forget, I better get the mass of the inflated balloon, because this is one of my major measurements that I need to get before the balloon pops. Okay, so here's the balloon, and here's the balance. The problem is that I can't really get the balloon on the balance. It'll be touching the ground. Okay, so what I can do is I can space it out with this little paper cylinder and lift it up so it is now off the table. Now remember, oh wait, if I put this on it, look at what's happening. What am I getting there? If you can't see from your angle, I think you can see it. Oh, that's the mass of, oh yeah, that's the mass of this. I don't want the mass of this. So I'm going to tear it or zero that out. So now what is the balance ignoring? It's ignoring the mass of the cylinder, right? So if I put this on top of it, and as long as it doesn't touch anything else, let it settle down. Okay, I'm getting the mass right there. I'm getting the mass of the inflated balloon. The mass of the inflated balloon, which goes right here, number 6. Mass of the inflated balloon. I had already jumped ahead and got the temperature. So now let's see, what do we have? We have the height of the balloon, we have the circumference of the balloon, we have the temperature of the balloon, and we have the mass of the inflated balloon. We also had the mass of the uninflated balloon. I think that's everything we needed. because now if the balloon pops, it's no big deal. I've got all my data. So how are we going to turn these numbers into things we can use in the ideal gas law? Well, one thing we can do, easy, turn the temperature into Kelvin. Remember that Kelvin measures the total temperature all the way. Here's 0 degrees Celsius. Celsius measures how far you are above that. So what were we? We were like 22, so that would be like about here, okay? Somewhere around here. Okay, that's about where we are in Celsius. However, Kelvin measures how far you are from the real bottom, absolute zero. Remember, in Celsius, you can go 100 degrees below zero, you can go 200 degrees below zero, you can even go 250, but you can't go further than 273 below zero, minus 273, which is absolute zero. And that's just a little bit colder than where helium becomes a liquid. Okay, notice where hydrogen becomes a liquid, neon becomes a liquid. It's interesting where these things boil. If you're going this way, they're boiling. Okay, just above absolute zero. So when we measure absolute zero, well, the number is going to be way higher because that's the total temperature. And of course, we need the total temperature in gas law because gas laws are proportional to the amount. So pressure has to be proportional to the total pressure, volume to the total volume, and temperature to the total temperature. And I guess you could say moles to the total moles. Okay, so now we've got to take our measurements and find the volume of this balloon. Okay, we've got our mass now, so I can put this off to the side. That's all we needed that for. Okay, so let's see. We're going to use this equation for the volume of a cylinder. And so if I take my circumference, and if I turn it into diameter and into radius, I can plug it there. Don't forget to square it times itself. And then times h, which was the height. Remember, think of it standing up for height. And then times pi, and that's my volume. Now volume, we measured it in centimeters. So centimeters squared times centimeters cubed is what we're going to get there. But remember, in the gas law, it needs to be in something else. So there is a step on here. Once you do get the total volume, you're going to be converting it. You're going to be converting the volume from cubic centimeters into liters. Okay, so don't forget, there's 1,000 cubic centimeters in a liter. So you're basically dividing by 1,000. Don't forget to do that, or your gas law calculation comes out crazy. One more little piece of volume I want to add to this, because actually the whole balloon is not like a cylinder. The very, very end is like a little bit of a dome. Imagine that that's like a bowl shape on the end, like half of a sphere. Oh, but wait, on the other end, we've also got a little dome, and that's about half of a sphere. Well, we know how to get the volume of a sphere right here. Volume of a sphere is one of the most beautiful equations in math. This is really 4/3, 4 over 3, but I just divided them. 1.33 is 4 divided by 3. The volume of that sphere would actually be pi r cubed. All you need is r to do that. Now r is the same r that we had for our whole cylinder all the way through, the radius from the middle out. It's the same radius for the spheres on the end, so you just cube it. R times r times pi times 1.33, and that's not going to give you a huge number, but that will be a little bit of an adjustment for your total volume of your balloon. So once you plug your numbers into here and then into here, add those together, then you've got the volume of your balloon. For the pressure, well, we're going to assume that the pressure in this room is about 1 atmosphere. Actually, if you want to be more technical, here's the pressure for today, the day I'm measuring it. This is pretty close to 1, but if you want to be a little more technical, then you can convert this into, what's the unit we need here for pressure? Remember, we have to convert it into atmospheres. So if you convert this into atmospheres, it's going to be pretty close to 1, but it'll be a little more accurate, just slightly off. Notice the conversion factor there, 760. Notice how close that is to 760. So it should be slightly less than 1. So you might say, well, we already know the pressure. So it's asking me for the pressure inside the balloon? Well, we already know the pressure. Actually, no, we don't. We know the pressure outside the balloon. If a balloon is inflated, if you inflate something, then the pressure inside must be larger than the pressure outside. Otherwise, what's going to push the material, the elastic material, to expand? What's going to push it into this shape? And then it reaches a balance, it stops expanding. So there's got to be more pressure inside this balloon than outside the balloon. So when we figure out the pressure inside the balloon, it's a little tricky. What we need to do is calculate the number of moles inside the balloon first. Remember, moles is the key to stoichiometry, and it's the key often to gas laws as well. Usually, one of the things we find first is moles. So how are we going to find moles? Well, remember, when we use this balance, let me put this balance back here. When we use this balance, we zeroed things out. We zeroed out this cylinder, right? But what am I zeroing? So right now, I'm zeroing out the cylinder. But what am I zeroing out right now? I'm actually zeroing out the entire pressure of the Earth's atmosphere. Because remember, pressure pushes on things. It even pushes on the pan of this balance. So when we zero a balance, we're actually ignoring all of the Earth's atmospheric pressure, which is very close to 1 atmosphere, slightly below today. It's a low pressure day. So do you know what? When I measured this on here, when I zeroed that and measured this, when I did that, I wasn't actually, it's touching something. I wasn't actually getting the total mass of this balloon, because some of the mass inside this balloon is already being zeroed. Imagine, before I inflated this balloon, there was air in that exact same space. The exact same volume occupied by this balloon would have been filled with air in this room. So I could calculate how much that is, can't I? Because I know the volume of my balloon now after doing all the geometry. I know the volume of my balloon, okay? And I know the pressure in the room right here. I could figure out how many moles are inside that balloon that I'm not registering on my balance. That's what I'm calling N base. So if you look on this sheet, okay, I lost my arrow here, where it says N base. N base is a calculation you're going to make using the temperature. You can assume you can also measure the temperature of the room. Okay, it's the same, 22.5 degrees Celsius, same thing. Temperature in the room, the pressure in the room, the volume of your balloon, and of course our old friend R. And we're going to calculate how many moles would have been there anyway. That's N base. Then you're going to calculate how many extra moles are in there. Moles that are more than what would have been there if we hadn't inflated the balloon. Moles that we sort of added to that volume to inflate the balloon. Well, that is what shows up on the balance. That's the mass that shows up on the balance. But remember, the uninflated balloon, of course, the uninflated balloon had its own mass. So you don't want to know that stuff. You don't want that. This one might be slightly different. Okay, each one is slightly different, of course. You don't want that material. Oh, so we better subtract it. That's the reason why we have the uninflated balloon and the inflated balloon. Okay? So the mass difference right here, you're going to calculate by subtracting. It's going to be a very small mass difference. This is number 7. The reason it's so small is because gas is really light. Gas is rare. It's rare air. Okay? Using that mass difference, that's grams. Well, I can turn grams into moles. How do you get from grams to moles? Molar mass. But then you have to calculate the molar mass of air. The molar mass of air, okay, is a little tricky because air is not just one chemical. It's a mixture of chemicals. So to calculate the molar mass of air is one of the trickier things on this lab. Okay, in order to do step 10, you need to use these percentages and the molar mass of each one of these. You'd multiply the percentages times the molar masses, and then you'd add up all the contributions. Now remember, these have to be in decimal form. This is percent. Percent means out of 100. So to use these, you have to put them into their real decimal form, which is dividing them by 100, or moving the decimal over twice. Do that first. Calculate the molar mass of each one of these, multiply through, and add up all the contributions. That's the molar mass of air. Once you know the molar mass of air, you can go from grams to moles, and you can get what we call the N difference. N difference. So the N difference is the extra moles that are inside the balloon, more than that space would have had anyway if the balloon wasn't even there. And then you can add those together, that's your total moles. And guess what? Once we've got the total moles, well then we can plug it right in this equation. Don't we already have the temperature and we have the volume of the balloon? And we can solve for the pressure inside this balloon. That's the last thing we do on this sheet. The last thing we get to on this sheet is the pressure inside the balloon. That's your final answer, and then you just rewrite them there. These are the same ones you rewrite and maybe round them off to the right place, make them look nice. So in order for this answer to be right, our final answer, well, the pressure, well, first of all, the moles is not going to be a big number. It's going to be like 0 point something. Because remember, the volume of a mole of gas is 22.4 liters at STP. This is nowhere near that. This is very, very tiny compared to that. So we don't expect this to be a mole. We expect N total to be 0 point something. In order to avoid over rounding, in this case, I would keep many, many digits. I would keep the zeros, and then after the zeros end, like 0.000, then keep 3 more numbers after the zeros end. That's a good way to make sure you're not over rounding. That's keeping things to the hundredths place in scientific notation. But just keep all the zeros, and then when you start seeing numbers that are not 0, keep at least the first 3. That's a good way to avoid over rounding all through these calculations. And then your final answer, well, you could probably, for the moles, you could write it like that. For the pressure, you can just round to the hundredths place, okay, in your answer. But you know the pressure inside the balloon has got to be more than the pressure in the room in order for this to be inflated. So if your pressure winds up, okay, less than what this turns out to be in atmospheres, well then you know it can't be right. So double check your calculations. So it's kind of a tricky pathway to get to these answers. And then on the other side, well, we've got the spherical balloon. It's almost the same thing, but with a spherical balloon. I'll probably make a separate short video to show you that one. That's on the back side of the paper, okay? So that's how you do the balloon lab. It's a little tricky, so think about it. Be very careful, and then don't over round, especially with these mole calculations. Keep many digits and 3 numbers after the zeros. So that's how we do the balloon lab.